Okay. Hey, a quick warm-up here. Number one is a little easier to see when we take log of, this would be log base 5. Let me change that so it actually looks correct. Log base 5 of 11 minus log base 5 of 30. So just a quick review, we can plug these pieces in. That is 1.490. And this is minus 2.113, which gives us a grand total of negative 0.623. I'm doing my best. I'm going to try to curl those a bit more, so lowercase l, but I am in a bad habit of putting capital L there. Okay? So, there we've got it. This one, 330 times, so 11 times 30, right? Okay, so if you do log base 5 of 11 plus log base 5 of 30, that multiplies. 11 times 30 is that. Okay. Everyone know the trick for 11s? We can come back to it here in a minute, but when we add these two pieces up this time, that gives us 3.603. Just on a side note, that has nothing to do with logs. If I'm doing 15 times 11, my answer is, if I'm doing 22 times 11, my answer is, if I'm doing 37 times 11, my answer is, check my work. 2. Cool? Yep. All right, anyway, just a side note. Okay, so this would be 11 by 11, right? Which multiply that 121, which means you're adding those two up. Okay, expanding this, we would on the top have the natural log. I really have a hard time with that. I don't like just putting, okay, so you have the natural log of 15 plus the natural log of x to the 12th, which I am going to move that 12 out in front, so it's actually going to be plus 12 natural log of x, using the power property. And then I am going to subtract from that the natural log of 2 and the natural log of y. Now you could either write it like that, subtracting both, or you could write it like that, with a plus.
Do you have to put the 15 and x in parentheses as well?
Right here?
Yeah.
No. Because multiplication would carry through. Even if it's in fraction, it would be due to the numerator. Okay, condensing this. Notice you have to have the same coefficient. So that's 1, that's 2. They're all log base 10, but we have a 1 and a 2 and a 1. So we want to, in this case, move that 2 in first. Okay, so you're going to have, this part is going to become log base, or log of 5 squared, or another way of thinking of it is a log of 25. Okay, so now we have log 10 plus log 25. That's log 250, because you multiply the 2 when you were doing addition. And then we're dividing that all by log 5, which is right there, which ends up giving us log 50. Yeah.
So you divide first and then multiply.
Sure. You get the same thing. Yeah. Okay. Next one, evaluate log base 2 of 9 using common logs. Okay, that means, what's the common log? Common log is base 10, so we would write that using the change of base. So for those of you who are like, what in the world are they talking about? That's what they're talking about. So you make it the common log or base 10. Okay, and then you put it in your calculator, you would end up with approximately 3.170-ish.
So would logs made so that people could do like big old numbers without calculators?
Well, you have, it's your inverse of your exponent. Yeah. So I don't think that was the intent. Like someone said, hey, I want to do big long numbers without my calculator. But they're just the inverse of an dealing with exponents. All right, evaluate log base 4 of 20. Okay, using natural logs. Natural logs is base e, which we like to call ln. Okay, so using the natural log, we would write that then of ln of 20 and ln of 4. Evaluating those actually would be approximately 2.161.
Wait, I still got the same answer, but I punched the log into my calculator.
Yep, you could, right? No matter what base you change it to, you're going to get the exact same thing.
Okay.
It's just they wanted you to change to natural log. Okay.
Will it matter like on the test?
Depends if you're asked to write it out in this format first. Okay. If you don't have to write it out, then no, it doesn't matter. Okay, so to continue our fun journey with logs, our fun journey down the river on the log. That didn't work too well. Hey, solving exponential and log equations. So now that we know how to work with exponential functions and log functions, we're going to solve equations with them. So, first step, I want you to work with your partner to complete exploration 1. All right, there you go. Okay, here we go. Hey, taking a look at them. First, those are the solutions that I have. Now, that is the actual solutions for x. Those are the actual solutions, approximate. Please note that what I was looking at is y sub 1 would be e to the x, y sub 2 would be, or y sub 2 would be y equals 2. And if I were to match that with graph C, notice this is the line y equals 2. This would be the curve y equals e to the power of x. Has a growth. I can tell it's a growth of, looks like as I go over to x equals 1, I have about 2.7-ish. Okay, so 1, 2.7 help me out there. My y-intercept, or x, excuse me, the intersection of the graphs about 0.7. Rory? So like y equals 2? Yeah. It represents this line. So all you're doing really, like if you were to think of this in terms of a system and graphing it, so let's say I take the first one and graph it. So in my calculator, I would actually put batteries eventually. Okay, I would have that. My first function would be one side of the equation. So y equals e to the x and y equals 2. Using substitution, I know that e to the x then equals 2. Right? So you're just doing a system of equations where if you graph them, you end up with that line. Okay, you have. Yep. Correct. So the solution would be where they intersect. And so if we wanted to actually use our graphing calculator calculator on it, you could. Oops, except for you'd actually have to. Okay, so you get 0.69. I have 0.7. Okay. All right. Any other questions there? Yeah.
Well, if you find it on your calculator, and it says like first curve and second curve, like where do you like how you just found it on there?
So if you're doing calculate and the intersect and it says first curve, it's asking you, do you want this to be your first curve?
Oh, okay.
And second curve, do you want that to be your second curve? Even though y equals 2 is not a curve, it's a straight line, it's still considered a curve in our calculator.
Okay.
Then you, since there's only one point of intersection, you don't have to worry about the guess. Okay. So I've got A goes with C, B goes with F, C goes with A, D goes with E, E goes with B, and F goes with D. You get x equals 0.7 for A, 0.4 for B, 0 for C, 4 for E or D, 2.2, and 1/2. It's where those lines intersect. Okay, so I've shown you how you can actually do it using a calculator, right? So the next exploration 2, says show how you could use a numerical approach by creating a table, and then how you can use more of an analytical approach. Well, if you're creating a table, and so let's say we use what I've done here and we go into our table, it's kind of tough to see where they intersect, especially if it's at 0.7. Okay, but you could keep narrowing. You could go to table set and go, okay, rather than going up by 1, maybe I want to go up by 0.1 or something. I mean, obviously at this point you would say, hopefully you would know that it has to be on the line y equals 2 somewhere, and it doesn't mean it's x equals 2. Excuse me, I should have put 0 there. Okay, but you go through here and you're like, all right, well, is there a way to tell where they intersect? Well, you're trying to find out where they have the exact same value. It looks pretty darn close right there. And so from that point, you can narrow in more. You can go, well, okay, I'm going to go up by now, rather than 0.1, maybe I'm going up by 0.01. Okay, doing it this way is quite tedious. Okay, so there you got it. It's getting even closer. Notice you go over it there. So it's somewhere in between 0.69 and 0.7. Okay, that's kind of a tedious process, using a table like that. Okay, an analytical approach would mean like actually solving using inverse operations. So how would I solve that using inverse operations? Okay, now the rule you need to remember is if you cannot solve it as an exponent in exponential form, then write it as a log. So if I write this log over base E and move it over, that's x equals natural log of 2, which you could do. You put the natural log of 2 into your calculator. Everyone go ahead and do that. Woohoo! You get 0.69, right? Approximately. Which way is the fastest? Yeah, probably more the analytical approach. Okay? It's up to you. How can you solve log equations and communicating? I'll let you answer that on your own at some point, but I want to go through these 6 problems together. Okay? So, number 4, I want you to give A and B a go. Okay, so let's just start with those first 2. All right, so you're doing letter A, and please make sure that you're not, the only logs that you use are the common log and the natural log. Those are the only ones you'll have access to when you're doing your quiz or test. Okay, so first thing to do on this one, use properties. These are both base what? Base 2. This is 2 to the 4th, So 16 becomes 2 to the 4th. And we have our x out here. And we have 2 to the 1st. Okay? Which means if you're at the same base, your exponents have to be equal. 4x equals 1. So x is 1/4. Okay, which approach did we use? Well, I used properties there. I found the common base. Okay, you could have went other routes. You could have graphed it and found the point of intersection. However, remember, you're not going to be using your graphing calculator on your quiz. So you have to graph it by hand. Yeah?
Could we use log on there with just log properties?
Sure, yeah. You can go that route. Yep. If you wanted to write it in log form, that would be log base 16 of 2. And use your log properties. Or maybe you write it as x equals log base 16 of 2 and write it in log form. You're like, well, I still don't know that, but however, I know how to use my calculator, and I know that log base 16 of 2 is log 2 over log 16. Right? You choose the change of base formula. And that would give you 1/4. Yep. Actually give you 0.25, and you'd have to change it to 24. You can do it. Questions there? All right, letter B. They're both base 2. Okay, so 4 is 2 to the 2nd. And then we have 2x plus 1. And we have 2 to the x. Once again, you have that is equal to that. So x equals 4x plus 2. Okay, so make sure you note this is 2 times 2x plus 1. Negative 3x equals 2. So x equals negative 3/2. Or negative 2/3, excuse me. Once again, using the properties and common bases help out. So using common bases is a good strategy if you can get to a common base. Any questions on those two? All right. Well, let's look at number 3, or letter C, I guess. Can you get a common base of 2 and 3? No. Okay? Well, 1, right? Okay, but you're still 1 times 1 times 1 times, right? You're still not getting 2. Okay. So 1 goes into both of those, but all right. So another strategy that I use is just like we've done in other sections where we'd impose a square root, I will impose a log. Okay, so if I have a number here and I really want to get that and the variables in the exponent, I want to get the variable out, I'm going to take the log of both sides. And then usually sometimes we start going, well, is that legal? Can you do that? Yeah, you can do that. Okay, as long as whatever you do to one side, you have to do to the other. Okay? So we've got that. Now, after we do that, go ahead and tell your neighbor what you can do now. Okay.
Oh, you can move the things out front.
Use the power property. That's me. You have to move the whole x plus 1. Ah. That's so fun. Okay. And now, note, log base 3 represents a number, right? Or excuse me, not log base 3. The log of 3 represents a numeric value. Okay? So if I'm going to put all this stuff together and try to get x by itself, first thing I need to do is distribute this log. So we're like unsimplifying here, if you want to think of it that way, kind of in a way. So we're bringing this in. We're going log of still log of 3, right? Where's the x go? Yes, the x is right out here. Okay? I tried to mislead you a little. Okay, so it's x log 3 and just log 3. And you have x log 2. Okay, tell your neighbor what you do from there. Okay, notice you have the same coefficient right here and here. So I'm going to move all my x's to one side. So I have x log 2 minus x log 3, and that equals log 3. Now that I have the same coefficient, I have the same base, I can apply the quotient property here. So that is x log of 2/3. And that is equal to log of 3. How do you get x by itself? You divide. Okay? So you would end up with dividing by log of 2/3. You get x equals log 3 over log 2/3. Which is approximately that is a fun one.
Oh my goodness, no.
Hey, so you could have graphed that one. However, you need to be able to put it on a graphing calculator or graph it by hand. There's the analytical approach. I promise you letter D is a little easier, but before we go on to that one, any questions on C? Okay, D. Give D a go. Remember the rule. If you can't solve it in log form, change it to exponential. Okay, so since that's log base 10 of 1/2, we move it over. We end up with x equals 10 to the 1/2, which is the square root of 10 if you want to think of it that way. Anyway, x is approximately
3.162.
all right.
I did that all on my own.
Okay. All right. Letter E. Tell your neighbor what you're going to do. Okay, we move that over, we get E squared. So x equals approximately 7.389, so we'll go 9. Cool. Those last two are so easy compared to letter C. Let's try letter F. Okay,
so the first one and the second one were kind of hard. D, E, and F were really easy. Where did C come from?
Well, it comes after B and before D. Yeah. All right. It's also the longest side of a right triangle. Okay, that is C.
Hypotenuse.
Yeah, hypotenuse. See what I mean? Okay. Want you to take a look at page 181 and 182 of your student journal.
Yep.
Page 181 and 182. 1 second. Okay. That is your assignment tonight. Okay. You're going to do your best. Oh, I'm sorry. 182 and 183. My apologies. Oh, man. Sorry. 181 was just a bunch of boring information. You need some... Oh, good, useful information. Yeah, that's probably good stuff right there. Okay?
Probably.
Yeah, probably.
High probability, but there's a